So, so in last class, we discussed about various activation functions, and today we will see loss functions associated with, we can say, machine learning and deep learning. So today you may find several loss functions related to uh, uh, different tasks. You may say, like, for example, if you are doing segmentation in computer vision, then loss functions like special loss functions are available. If you are implementing simple machine learning models, then we may use traditional loss functions. Then for deep learning also, new loss functions have been introduced in literature. So today, first I'll discuss the most traditional loss functions, the classic loss functions which we use when we implement this models. So let me first tell you that what is loss function and why is it required. Okay. So I would like to let you know that you might have heard the different words for loss function like error function, cost functions, because this loss function, it is these words are used interchangeably, and this loss function is also called uh, error function. It is also called cost function. So this loss function is very important in machine learning or deep learning. Let us assume that you are working on any problem and you have trained a machine learning model on the data set, and you are ready to put it in front of your client, or you are ready to deploy it for real-time applications. But how can you be sure that the model which you have trained using data will give the optimum result? How can you be sure that this is the good model? It will give optimal results. So the question is there a metric or a technique that will help you quickly evaluate your model on the data set? So the answer is yes. We can use loss function in machine learning and deep learning to evaluate model on the data set. So now let's see that how can we use this loss function. In mathematical optimization and decision theory, this loss function, which is also called cost function or error function, is a function that maps an event or values of one or more variables on the real number, representing the cost associated with the event. This is in mathematical terms, mathematical optimization, right? In simple terms, or in machine learning, deep learning terminology, we may say that loss function is a method of evaluating how well your algorithm is modeling your data set. How well your algorithm is modeling your data set. Now, it may be any algorithm. It may be, say, for example, SVM, support vector machine. It may be naive Bayes. It may be like you are implementing or you are training a machine using neural network. So it determines that how well your algorithm is modeling your data set. It is a mathematical function of the parameters of the machine learning algorithm, right? Why we are talking about the machine learning? Because we know that deep learning is subset of machine learning. So we can use these loss functions even if we are solving problems using deep learning algorithms. So there are several loss functions. So I hope you have understood that what exactly the loss function is. Okay. I give you another example, or you may say analogy to understand this concept. Assume you are given a task to fill a knapsack, or you may say to fill a bag with 10 kg of items. You are given a task to fill a knapsack with 10 kg of items. Now you fill it up till the measuring machine gives you a perfect reading of 10 kg, because you can fill maximum 10 kg in your knapsack or in your bag. Okay. So you'll keep on filling that bag until your measuring machine, weighing machine gives you a perfect reading of 10 kg, or you take out the items if the reading exceeds 10 kg. Okay. So just like that weighing machine, if your predictions are bad by the machine learning model, your predictions are bad by the machine learning model, your loss function will output a higher number because predictions are not good. So your loss function will output a higher number. If predictions are pretty good, loss function will output a lower number. I hope you are with me. If predictions made by trained machine learning model are good, then loss function value would be low. And if the predictions are bad, then loss function value would be higher. So as you experiment with your algorithm to try and improve your model, your loss function will tell you if you are reaching, like if you are getting anywhere or if you are reaching anywhere. So loss function tells you, like when you during training, that where you have reached. So in short, we can say that the function we want to minimize or maximize is called the objective function or criterion. And when we are minimizing it, we may also call it the cost function, loss function, or error function. So cost function is a function which we, or this loss function is a function which we want to minimize, which we want to minimize. At its core, we can say that a loss function is a measure of how good your prediction model does in terms of being able to predict the expected outcome. So we convert the learning problem into optimization problem, define a loss function, and then optimize the algorithm to minimize the loss function. So that you can see in the diagram, which is mentioned on the which is the diagram which mentions the steps which we have just discussed. You can see in this diagram on the right hand side that different layers are there in neural network. Let's say we have two hidden layers. So you can see that input X goes to input layer, and then these are the different layers, like so layer one, layer two, weight values are introduced, and then prediction at the end, output layer, right? You will have a y-des, which is predicted value. Now, if it is supervised learning, there is also a target value label which is given to you. So from that label, like from that target value, you will calculate loss. Like y-des and y, you will find the difference between them, and that difference represents the loss. Okay, and then like loss score, and accordingly, changes will be made in the next iteration of the training. So this is about like brief about the loss function. Mainly, there are two types of loss functions: regression loss functions and classification loss functions. Now, this also, those who have studied machine learning, they might be knowing about these loss functions. So we have different types of loss functions: regression loss functions and classification loss functions. Now, there are not only two regression loss functions or two classification loss functions, but I have included here popular loss functions, right? Otherwise, today you'll find like some other loss functions too in literature. I'll tell you their names, and later you can search them in Google and you can explore them. But these are the popular loss functions used with most of the regression problems and classification problems. Okay. So here I have included some more, like these are the loss functions in deep learning. You can see that. So for regression problems, we may use mean squared error, mean absolute error, Hubbard loss. For classification, binary cross entropy, categorical cross entropy, apart from hinge loss is there, like many other loss functions are there. For autoencoder, KL divergence is there. For GAN in deep learning, generative adversarial networks, discriminator loss and min-max GAN loss. These are the two different losses available. For object detection problems, like focal loss is used. For word embedding problems, triplet loss is used. So as I told you, these are not only the loss function. Sorry, I think I am on the same slide. Yeah, sorry, I forgot. So here you can see that these are the different loss functions available in deep learning, right? So you can see that Like this, again, these are not only the loss functions available. If you refer to literature, you will find some more loss functions. And this is also a very good area of research. Like my PhD scholar recently, he proposed a new loss function. Like some loss functions I have not included here, IOU loss, then Tversky loss. These are also loss functions. So as I told you, these are commonly used loss functions, which I have mentioned in this slide, but there are many loss functions available in literature too. So later you can, like if you do research or if you do project in this subject, then you can refer to literature to find more loss functions and to find loss functions suitable to your problem. So, okay, now let us cover the commonly known, the traditional loss functions, which are MSE, MAE, Hubbard loss, binary cross entropy, categorical cross entropy, and hinge loss. So let us discuss them, and later uh, you can refer to literature to know more about the other loss functions. Okay. So mean squared error, it is like mean squared error. Mean squared error is the workspace of basic loss functions, as it is easy to understand and implement and generally works pretty well for majority of the problems. And you can see that very simple formula to calculate this mean squared error. You take the difference between your model's predictions and the ground truth, or model's predictions and target value, and square it out and then average it out across the whole data set. So that's why here you can see that yi and yi dash. Yi is the target value, that is given value, or you can say label given in data set, which is also called ground truth. Here I am using these words interchangeably. You can notice these words: ground truth, target value, or I can say label, right? So these are like, that is yi. Yi dash is predicted value. So first we are finding the difference between yi and yi dash. It is squared. Okay, it is squared, and then we are taking average on all the records in data set. So let's assume there are n records in data set. Then we are finding first, and we know that to find the average, we first sum up all the values and then divide it by n. So that's what we are doing. This is called mean squared error because we are squaring the error. Okay, and then we are finding the mean. We are first squaring the error, okay, and then we are finding its mean. So that's why its name is mean squared error. It is also called squared loss or L2 loss. These are the these are the words used interchangeably for this type of loss. Okay, so advantages are, here you can see that this is very popular and works for most of the problems. The result is always positive when we use this loss function, regardless of the sign of the predicted and ground truth values. And a perfect value is like 0.0. Of course, we want zero error when we train our model. We expect zero error. Zero error means model is like most accurate model. Okay, when there is error is 0.0. So that is the perfect value for this loss function. Okay, and here you can notice the advantages and disadvantages of it. So it's very easy to understand that what are the advantages and disadvantages of this mean squared error. Advantages are that it is easy to interpret, of course, because just we are finding the difference, squaring it and finding the average. Always differential because of the square, and only one local minima. So no confusion. Disadvantages are that error unit is in the square. Error unit is in the square. And because the unit is in square, it is not understood properly. Like error cannot be understood properly because it is in square. So we don't know like whether it is we are getting negative value, positive value. When we subtract the predicted value from the target value, we don't know whether it is negative or positive because ultimately we are squaring and it becomes positive. So that's why it is very difficult to understand this error properly, and it's not robust to outlier. So outlier is a term usually uh, used in data science terminology. Outlier means very different value in the exceptional value in the data set. So for example, if I give you example, if I give you example, suppose I think I gave you the same example that suppose exam of deep learning subject is conducted and exam is conducted for 100 marks, and most of the students they scored marks between say 40 to 70 out of 100. But there are two students in class who scored say 95 and 87, 95 and say 99. Okay, and two students they also scored marks of 5 marks out of 100, and let's say 11 marks out of 100. Okay, so we know that what is the common range? Common range is 40 to 70. Most of the students they scored between 40 to 70, but four students they scored out of this range. Two students scored 5 and 13, and two students scored 92 and 99. So these are exceptional values and they are like outliers. Okay, they are out of the range. They are out of the range and they are called outlier. Okay, so this loss function is not robust to outlier. Okay, so these are the limitations of this loss function. Okay, now let's move to the next loss function, which is mean absolute error. Mean absolute error. It is also known as L1 loss. It is also known, this is L2 loss and this is L1 loss. You can notice the difference here. See the difference between these two. Mean absolute error. Can anyone write in chat box what is the difference? You look at the formula of mean squared error and look at the formula of mean absolute error. And tell me the difference from this formula. You may write in chat box. So I'll come to know whether you are with me or not. Yeah. Okay. Yeah. So you are absolutely right. That difference is that here, instead of, now you see that this is L2 loss and oh, sorry, this is a L1 loss and this is L2 loss. So here we are squaring. Okay. And here we are finding the absolute value. Here we are finding the absolute value in L1 loss. So that is the main difference between this two. The mean absolute error is also the simplest loss function. And to calculate it, you take the difference between the actual value and the model prediction, and you average it across the whole data set. So we are just finding the difference and we are averaging it over the whole data set. That is mean absolute error. Fine. So the advantages are clear and they are mentioned here, advantages. Okay. So just you go through, I'll discuss them. But interestingly, provides the almost this mean absolute error, interestingly provides almost exactly opposite properties. To calculate this MAE, like we take the difference and apply the absolute value to that difference and then average it out across the whole data set. So results are like, though difference seems very minor, but the results are very different when we use it. The advantages are this is intuitive and easy. Error unit same as the output column, and it is robust to outlier. So one of the disadvantage of L2 loss is overcome by this MA, by L1 loss. And that disadvantage is previous one, L2 is not robust to outlier, while L1 loss is robust to outlier. But the disadvantage is that it is not differential. We cannot use gradient descent directly here, and then we can subgradient, we can use subgradient calculation. So that is the disadvantage here. Fine. And now if we move further, then next we have Haber loss. Okay, now what is this Haber loss? Okay. In statistics, this Haber loss is a loss function used in robust regression. It is used in robust regression that is less sensitive to outliers in data than the squared error loss. This is less sensitive to outliers in because the previous two, especially the first one, L2 loss, it is sensitive to outliers. But this one, this Haber loss, is less sensitive to outliers in data than the squared error loss, that is L2 loss. We can use any of this formula to calculate this Haber loss, where n represents the number of samples, number of data points, number of records. I'm using this different words here. See this, n represents the number of data points or number of samples, okay, number of records. Y represents the actual value of the data point, that is target value. See, one more word is introduced. Earlier, I told you that target value, ground truth, these words are used interchangeably. Okay, target value and yeah, that ground truth. It is also called actual value. So Y represents the actual value of the data point and also known as true value, ground truth value. Okay, Y hat represents the predicted value of the data point. And this value is returned by the model. It is predicted by the model, that is Y hat. And then we have we have this raw, which is defines the positive. It defines the point where the Haber loss function transitions from a quadratic to linear. So these are all symbols used in this formula. You just need to put values of all this, right? It's very simple. How to how can you calculate the Haber loss? So this is how it is calculated, and advantages are this is also robust to outlier like MAE and unlike MSE. Like MAE and unlike MSE. It lies between, its performance lies between MAE and MSE. However, the disadvantage is that it is disadvantage is it's also a complexity in calculating this loss. Compared to MAE and MSE, the computation of this Haber loss is complex. So in order to maximize model accuracy, the hyperparameter raw will also need to be optimized, which increases the training requirements. Matlab, as you train your model, you will be able to optimize this hyperparameter because this is considered as hyperparameter, and we know that hyperparameter tuning is required to find the optimal value of hyperparameter. So if you get the optimal value of this parameter, this loss function will work good, and to get its optimal value, you need hyperparameter tuning. So this is about the Haber loss. Now, these are the commonly used loss functions for regression problems. These are the commonly used loss functions for regression problems. Now, if we talk about the classification problems, we also have some classic loss functions for classification problems. So let us start with a very popular loss function known as binary cross entropy or log loss. Binary cross entropy or log loss. It is used in binary classification problems. Binary classification problem is problem having two classes, yes or no, whether patient is suffering from disease or not, male or female. Like for example, suppose you are feeding image to train model, and its task is to predict whether image contains male image or female image. So it is binary classification problem. Cat and dog classification only in two classes, cat and dog. It is binary classification problem. So this is used in binary classification problems. And example like, yeah, I gave you example, like many examples I gave you, whether a person has COVID or not, right? So this is binary classification. Binary cross entropy compares each of the predicted probabilities to the actual class output, which can be either 0 or 1. I hope you know how this binary classification problem works, because when it is a classification, we calculate probability, and based on probability, the class is determined. So in this binary cross entropy compares each of the predicted probabilities to the actual class output, which can be either 0 or 1. And it then calculates the score. It then calculates the score that penalizes the probabilities based on the distance from the expected value, that how far it is from the expected value. So based on the distance, it penalizes the probabilities. And this means how close or far from the actual value. So here you can see that the formula is log loss is equal to first, like y minus probability is involved in classification problem. So yi and 1 minus yi are used. So yi is actual value, or you can say target value. You can say ground truth value. So yi represent the actual value or target value. So we calculate like yi and yi is given and 1 minus yi is also used. And like a predicted value, you can see that actual value yi and yi hat represents neural network prediction. So we are using this formula to compute this log loss. And advantages are this cost function is differential. However, the disadvantages are we may find multiple local minima using this function. Using this loss function, we may find multiple local minima, and this is not intuitive. In classification, like at least in classification problem, at last, neuron use sigmoid activation function that we discussed earlier, right? Okay, so this is about the binary cross entropy. Fine. Okay, let's move further. Any question till this point? Acha, where is y hat in this formula? Y hat, not HAT, that head, caret is head. Okay. So in this function, yi hat means yi and that caret is there. I hope it is clear. After log, see log and then yi hat. Okay. Fine. Okay. Any other question? Okay, local minima and global minima. Fine, I'll tell you local minima and global minima. Local minimum of any function is a point where the function value is smaller than at nearby points. It's smaller than the nearby points, but possibly it is greater than at a distance point. So and global minimum, we use both these terms, local minima and global minima. So global minima is a point where the function value is smaller than, I repeat, global minima is a point where the function value is smaller than at all other feasible points. And local minima of a function is a point where the function value is smaller than nearby points. So usually this is how we define them. Like global minima is the largest value in the whole function, and local minima is the largest value in a subset of the function. Local minima, that way also we define it. Local minima is a largest value in a subset of function. So you will find like if you have learned AI subject, you might have studied this difference, local minima and global minima. In short, the maximum or minimum over the entire function is called an absolute or global maximum or minimum. The maximum or minimum over the entire function is called an absolute or global maximum or minimum. Okay, so there is only one global maximum and one global minimum, but there can be more than one local maximum or minimum. I repeat, there is only one global maximum and global minimum. Global maximum and minimum is always one. But local maximum or local minimum can be more than one. It can be more than one. Okay. And MA is robust to outlier. Okay. How? So if you want to know, so what you can do, I suggest you, I think you have started experimenting practicals related to this subject. So I strongly recommend you take very simple data set from Kaggle or GitHub. Okay, download a simple data set. Very simple data set, maybe cat dog or some simpler than this also you can download. And you implement simple neural network model or any machine learning model with which you are familiar. Maybe support vector machine, maybe naive Bayes, maybe okay, you are talking about MA, so no classification model. You need to implement regression model. Okay, you implement any regression model, download dataset from there. You can use scikit-learn library of Python, right? Because I like it for some traditional machine learning problems. But if you want to implement deep learning related practicals, then I recommend TensorFlow and Keras for them. But for this machine learning techniques, you can use scikit-learn. These models are available. Now, what you do, you implement once using MA, implement once using MSc. Okay, and notice the difference. But consider data set with outliers. Outlier, I already explained you what is outlier. Uncommon value, right? Uncommon value. If the common values, like most of the records, in most of the records, you are finding the common value for a particular feature, but some of the records, they have like they have exceptional value for that feature, then that is called outlier. Now you calculate these errors for a data set having outlier and check that what difference you are getting in performance. Now here, what is performance? Performance means accuracy. If it is classification problem, performance is accuracy. Okay, what are the parameters used to measure the performance of regression problems? Can you write in checkbox? Can you write in checkbox? Because these concepts must be clear to you. When I started, I assumed all these concepts are clear to you. So like for classification problems, we use accuracy, we use confusion matrix, we used Arrow curve. Question is, which evaluation parameters are used to evaluate the performance of regression models, and which evaluation parameters are used to evaluate the performance of classification models? We use different parameters, evaluation parameters, like how you are measuring the performance of classification model and how you are measuring the performance of regression model. Yeah, you may write in chat box. So all this, like we are discussing, okay, graphical representation. Accuracy we use for classification problems, not for regression problems. Okay, graphical representation, linear. No, like we may say that performance is, because the performance is measured using this error measures, mean absolute percentage error, mean squared error, root mean error, R squared, then adjust square. These are all used to measure the performance. Fine. And for class parameters are different. Okay, compared to regression model. Okay, now when you implement, I recommended you to implement all these loss functions with one problem. You download dataset, implement this, and notice that how it is robust to outlier. Robust to outlier means compared to MSE, MAE gives better output when you use MAE for dataset having outliers. So how it is robust, that you can check, you can verify uh, via implementing it in lab. Parameter alpha is called the constant or intercept and represents the expected response when xi is equal to 0. So I didn't understand the question from this um, like statement. Okay, fine. So let us move ahead. Hinge loss. The next is hinge loss. Okay. It is also used for classification problem. Binary cross entropy used for classification. Hinge loss. It is also used for classification problems. Fine. Okay. So what is hinge loss? Let me tell you what is hinge loss. Hinge loss, like we can say that this is the second most common loss function used for classification problems, and it is an alternative to cross entropy loss function. This is primarily developed for support vector machine model evaluation. So this is one algorithm, machine learning algorithm for classification problem, support vector machine. And this hinge loss is developed for the support vector machine model evaluation. And this is the formula. It's very simple, like hinge loss, how it, f of x is predicted value, y is given value, and this is how it is calculated. Hinge loss penalizes the wrong predictions and the right predictions that are not confident. It's primarily used with SVM classifiers with class labels as -1 and 1. Usually with the classification, we use like binary classification, we use label 0 and 1. But when we use hinge loss, we use -1 and 1 to represent this. Okay. Then next we have categorical cross entropy. See, I'm discussing very like only popular loss functions, but again, I tell you that if you refer to literature, you will find several loss functions, right? Just I told you, अभी मैंने आपको बताया कि like other than this MSE and MAE, which are the other loss functions you can use for regression. If you remember, I told you that mean absolute percentage error can also be used. Root mean squared error can also be used apart from mean squared error, MSC and RMSC. Then R squared can also be used. Then adjusted R square can also be used, right? So several you will find in literature. Okay, now let's discuss the categorical uh, cross entropy. Categorical cross entropy is used for multi-class classification and softmax regression. So this is the function which you can use to calculate this loss function. It can be calculated using this first or second, like loss function and cost function. These words are used interchangeably, but these are the two different ways you can calculate it, where K is classes, like, because this is used for multi-class classification problem, while binary cross entropy is used for binary classification problem. So as this is used for multi-class classification problems, you have multiple classes, more than two. So that K represents the number of classes. Suppose I want to uh, classify given image in one of the, say, six classes. Which six classes? Cat, dog, donkey, horse, lion, tiger. So these are the six different classes. So K represents the number of classes, Y again represents the actual value, and Y hat represents the neural network prediction. So you can calculate using this formula. The question, you may have this question that when to use categorical cross entropy and sparse categorical cross entropy. We also have sparse categorical cross entropy. So if target column has one hot encoding, two classes, like now, what is one hot encoding? It must not be clear to you. One hot encoding. This is data science concept. Okay, let me skip this discussion that when to use categorical cross entropy and sparse categorical cross entropy, because you will be able to understand this if you have studied data science. Otherwise, it won't be clear to you. But okay, let me at least I can tell you which is faster. So sparse categorical cross entropy is faster than categorical cross entropy. Faster means here, what do you mean by fasters? Like it allows, like it helps us to, it helps model to converge faster. Okay. So if I tell you in summary, like we have not seen all the available loss functions. We have discussed very popular classic loss functions. And the key takeaways from the discussion of these loss functions are: we learned the importance of loss functions in machine learning and deep learning, differences between loss and cost, like differences, though these words are used interchangeably, I can tell you the, like minor differences between them. Let me tell you the differences. Loss function measures the error between predicted and actual value, while cost function quantifies the overall cost or error of the model. Loss function measures the error between predicted and actual, but that's its loss function. While cost function quantifies the overall cost or error of the model on the entire training data set. That is called cost function. Loss function used to optimize the model during training, while cost function is used to guide the optimization process by minimizing the cost or error. The next difference is loss function can be specific to individual samples. Yes, it can be specific to individual samples because we find the difference between predicted value and actual value. While cost function aggregates the loss value over the entire training set. So that is called cost because it is associated with entire data set. So cost function aggregates the loss values of individual samples over the entire training set. The next difference is examples of loss functions are mean squared error, mean absolute error, binary cross entropy. These are the examples of loss function. And cost function, often the average or sum of individual loss values in the training set is considered as cost function, right? Another difference, if I tell you, loss function is used to evaluate models' performance. It is used to evaluate the model's performance, that how model is performing, good or bad. While cost function is used to determine the direction and magnitude of parameter updates during optimization. One more difference I'll tell you. Loss function like different loss functions can be used for different tasks or problem domains. Like as we discussed, different loss functions are available for regression problems. Different loss functions are available for classification problems. Even in classification, if we are using support vector machine, we have a hinge loss, right? If it is multi-class classification problem, categorical cross entropy, binary classification problem, then binary cross entropy or log loss. So we have different loss functions which are used for different tasks or problem domains. If we talk about the cost function, typically it is derived from the loss function, but can include additional regularization terms or other considerations. So these are the differences between loss and cost functions. Yes, yes, you are saying that, you are right, that cost functions. Just a second. Battery is low. I need to switch on the. Oh, yeah. Thank you. Okay, so yeah, here, cost functions output is average of loss functions. So it's not average, but we can say that it is over the entire data set, right? So yeah, often the average of sum of individual loss values in the training set, it is considered as like a cost function. Yes, Hit. Fine. So if I tell you like these are the differences, so we have understood now difference between loss and cost functions. The mean absolute error is robust to the outlier. That also we have seen. This function is used for like which function is used for binary classification problem, that also we have seen. Sparse categorical cross entropy we have not discussed, but I told you at last that sparse categorical cross entropy is faster than categorical cross entropy. So like this is the summary of loss functions. Now, if I ask you like the difference between loss and cost, I am sure that you will be able to uh, just you will be able to tell what is the difference between loss and cost. But if I ask you what is L1 loss function in deep learning, that also must that also must be clear to you. Okay, that L1 loss function is mean absolute error, which is commonly used in deep learning. It calculates absolute difference. Then what is L2? So L1 loss is robust to outliers, but does not penalize larger errors as strongly as other loss functions like L2 loss. So benefits and disadvantages of all different loss functions must also be known to you. Okay. Now, if I ask you what is the loss function in deep learning for natural language processing? I didn't focus on it because we are learning deep learning for computer vision. Deep learning for natural language processing is a vast area, vast topic, and it is different. But just for your information, I will tell you in deep learning for natural language processing, various loss functions are used depending on specific task, that what task you are doing in natural language processing. And common loss functions for tasks like sentiment analysis or text classification, they include categorical cross entropy and binary cross entropy, which measures the difference between predicted and true class labels for classification task in NLP. So in NLP also we have classification tasks, and there also we use this categorical cross entropy and binary cross entropy loss functions. Fine. Now, if any point, let me, okay, or if you have any question, you may ask me. Quantile loss is also there. So many loss functions are there. Any question till this point? You can draw diagrams once you compute the loss function. Draw graph, plot it on the graph. to see the performance, that whether it is increasing, decreasing, or steady. So usually we use graphs to plot the loss function. Okay, so if no questions, then let's move to optimizers. I assume that there are no questions. Okay, fine. So let's move to optimizers. Okay, so if you are familiar with machine learning, then you might have studied this optimizers. So anyone knows what is optimizer in machine learning or deep learning? You can write in checkbox, or you can turn on your mic and you can let me know what is optimizer. Okay, we can say that optimizers are optimization method that helps improve a deep learning machine learning model's performance. This optimization algorithms or optimizers are widely algorithms widely affect the accuracy and speed, uh, training speed of the machine learning deep learning model. This optimization algorithms, they widely affect the accuracy and training speed of the machine learning deep learning model. But okay, so this is like optimizer or optimization method. So while training the machine learning deep learning model, we modify weight value during each epoch and minimize the loss function. This is to minimize the loss function. Optimizer is a function or an algorithm that adjusts the attributes of the neural network, such as weight value, learning rate. Thus, this optimizer or optimization algorithm, it helps in reducing the overall loss and improving the accuracy. Optimizer is a function or an algorithm that adjusts the attributes of neural network like weights and learning rates, and thus it helps us in improving accuracy and reducing the overall loss. So the problem of choosing the right weights for the model is a very tedious, like tricky task, as a machine learning model generally consists of millions of parameters. Deep learning models, like they consists of millions of parameters, so it's not easy to determine, or it's not easy to choose the right weights for the model. It tries the need to choose a suitable optimization algorithm. If you choose the suitable optimization algorithm for your application, uh, then this will help you to reduce the error and improve the accuracy. So the important terms related to machine learning and deep learning model, like epoch, sample, batch, learning rate, cost function, loss function, weight, bias. This all we have discussed so far. So now the only one term related to this machine learning and deep learning models is left, that is optimizer. Otherwise, the rest of the terms we have discussed so far. So let us quickly review the optimizers used for machine learning models. So very popular one is gradient descent optimizer. Like this is used for deep learning also, gradient descent optimizer. Gradient descent can be considered as the popular among all the optimizers. This optimization algorithm uses calculus to modify the values consistently and to achieve the local minimum. So uh, before like we move ahead, those who are new to this machine learning, deep learning, they may have questioned that what is gradient? Because we are discussing gradient descent optimizer. So what is gradient? In simple terms, consider you are holding a ball resting at the top of a bowl. And when you lose the ball, it goes along the steepest direction and eventually settles at the bottom of the bowl. So gradient provides the ball in the steepest direction to reach the local minimum, which is the bottom of the bowl. Okay. This a gradient provides the ball in the steepest direction to reach the local minimum. Local minimum is bottom of the bowl. So this how this is how the gradient is calculated. So there is a formula to calculate the gradient, which I have not included here, but this is what the gradient is, and gradient descent works. The first step is it starts with some coefficient, sees their cost, and searches for cost value lesser than what it is now. And then it moves towards the lower weight and updates the value of the coefficients. And this process is repeated until the local minimum is reached. And local minimum is a point beyond which it cannot proceed further. Okay. So before I move further, for this topic of optimization algorithm, optimizers. Can you please let me know that are you familiar with optimizers? Like, because I assume that you studied machine learning and you are familiar. Because if you are not familiar, then I need to include the diagrams of all this gradient descent and all to explain you what is local minimum and what is the plot of this gradient descent, because then only you'll be able to understand that how gradient descent works based for most purposes, most of the applications, though it
Uh,
has some
Hello,
downsides too.
hello,
Yeah.
madam. Students are not familiar with these fundamentals of
Okay.
optimizers, so I request you to put that diagram, whatever you want to.
Okay, okay, fine. So I think that should be discussed. Fine. So I have those slides in my different presentations. So next time, like in next class, I'll include those diagrams too. So through that diagram, you will understand that what is global minimum. Okay, so initial weight we can have, like through the diagram, it will be very easy to explain you that how we start with initial weights and how do we reach to like local minimum and what is global minimum. So that I'll tell you, because once the gradient descent optimizer is clear to you, you can easily understand stochastic gradient descent optimizer too, right? And we have also like other extensions of this. Like stochastic gradient descent with momentum. The first is gradient descent, then stochastic gradient descent, then stochastic gradient descent with momentum. So many optimizers are there. Mini batch gradient descent optimizer is also there. Then adaptive gradient descent, which is called EDA grade. EDA grade optimizer is also there. Okay, fine. So we can discuss this optimizers in next class. And meantime, if you have questions, you can like ask questions.